Okay, today we're covering reading number 9 on cycling biomechanics, and we're actually going to cover two readings today, numbers 9 and 10, our last and second to last readings on the cycling biomechanics section. We're grouping these two readings together, similar to when I grouped the two readings on pedaling rate together, in that study 9 here by Kautz and Hall and study 10 here by Cullen et al. Both cover similar topics. They both cover the sensitivity of cycling performance related parameters to the shape of the chainring, which we'll take a look at here in a little bit and define that if you're not familiar with what the chainring is and what its shapes typically are and are not. Similar to when we grouped the two pedaling rate papers together, one of which was a computer simulation study and one of which was an experiment on human subjects. Similar to that, paper number 9 here on circular and non-circular chain rings is a computer simulation study, and paper number 10 here is an experiment on human subjects examining how a cyclist performance is affected by circular and non-circular chain rings. In contrast to the two studies on pedaling rate, which generally had similar results, these two studies get different results. The first one finds a benefit in their outcomes for using a non-traditional chainring shape, and the second one didn't find that benefit, even though it examined a similar difference in chainring shapes. Doesn't necessarily mean one's right and one's wrong, doesn't necessarily mean the computer model was bogus, it just means they found different results, and then we can look at what's different between the studies and see if we can figure out why they found different results, and if we can take something away from both of them or from either of them. Okay, before we dive into either of them, let's take a look at a bike and see what exactly is a chain ring and what does it mean to have a non-circular chain ring. So I'll pull up my video here and let's point it at the bike. Get my junk out of the way here. Okay, so there's my bike again. And the chain ring is this front set of gears up here. Some bikes have 2 gears up here. Most like sport/race, training performance type bikes will have 2 gears up here on the chain ring, a big gear on the outside and a smaller gear on the inside. Bikes that are called fixies, which have just 1 gear, or even some bikes that have multiple gears but only shift the gear in the back, will sometimes just have 1 ring up here on the chain ring. But when you hear the term chain ring, that's referring to this front gear up here, whether you're on the big gear or the small gear, whether you have 1 gear up here or 2 gears, that piece on the bike is the chain ring. It's the part that you turn when you rotate the crank by pressing it with your feet, and it is connected to the actual chain on the bike, of course, which then connects to the cassette in the back here, which has this second set of gears, which is coupled to the wheel and presses on the road and actually rotates and moves the bike forward. Okay. So when we talk about the shape of the chain ring, whether it's circular or non-circular, this chain ring on my bike is, of course, a circular chain ring and has a circular shape to it. Okay. You obviously couldn't fit some arbitrary shape of chain ring on here. You're going to be constrained by the geometry of the bike, and you don't want it to be too big because then it gets heavy and might affect performance on hills and stuff like that, or might affect aerodynamics if it's some bizarre shape with weird edges sticking out here. So you often see bikes that have a circular chain ring like this. In fact, I think if you go out and look around in your community or at bike races, like when the Tour de France starts up here in a little bit, take a look at chain rings, and I'm pretty sure you'll see almost exclusively circular chain rings. You hardly ever see a different chain ring shape. Now, that's largely out of tradition, out of simplicity of manufacturing them, out of mass and aerodynamics and things like that. But there's no necessary reason why for some of the performance-related things we've been talking about, like crank power and efficiency and VO2 and economy and things like that, no necessary reason why a circular chain ring is necessarily the best. And let's see if I can demonstrate a hypothetical case of what we're getting at there. And I'll clip in here and start pedaling a bit. So as I'm pedaling my bike here, the main muscles that are important, let me move my screen up here a little bit, you guys can't see the top of the bike. Okay, that'll be a little bit better, I think. Okay, as I'm pedaling my bike here, the main muscles that are important for turning the pedals and producing the crank power that actually moves the bike forward are generally the same major muscles that were important for jumping and for supporting the body weight in running. The big, large, strong extensor muscle groups of the main three joints of the lower limb here. So the glutes, the hip extensors, for cycling especially the quadriceps, the knee extensors, and to a lesser extent in cycling, but still an important muscle group for the pedaling motion, the ankle extensors, the calf muscles or plantar flexors here. Now I'll slow down a bit so you can hopefully visualize this, but recall that as I'm moving here through my pedaling cycle, my angles of those three joints are changing, right? My hip angle is changing, my knee angle is changing, and to a lesser extent also my ankle angle is even changing a little bit. As those angles are changing, that is stretching and shortening the lengths of those muscles. The length of the gluteus muscles is changing as my hip angle changes. The length of the quadriceps muscles are changing as the knee angle changes, and also as the hip angle changes in the case of rectus femoris, the quadriceps that crosses both the hip and the knee. And then as my ankle angle changes and my knee angle in the case of gastroc here, those angles are affecting the length of my plantar flexors here, of my calf muscles on the back of my leg there. So the length of those muscles is constantly changing during the pedaling cycle. Since there's a timing element involved here, sometimes I'm pedaling real slow, sometimes I'm pedaling faster. Not just the length of those muscles is changing, but also the velocity of the muscles is changing. Sometimes they're being stretched quickly, sometimes they're being shortened quickly, sometimes they're being stretched slowly, sometimes they're being shortened slowly, sometimes they're more or less isometric and not really changing length at any appreciable speed. So because of those two kinematic factors, that throughout the pedaling cycle here, the length and velocity of my muscles are changing, that will change during the pedaling cycle where my muscles are operating on those force length and force velocity curves, which affects, for a given activation level, how much force my muscles can produce, how much power they can produce, and how much metabolic energy they're going to consume to produce a certain amount of force and a certain amount of power. Okay? So you might imagine that throughout a hypothetical pedaling cycle here, there might be like an optimal path or an optimal set of like time varying joint angles here that would cause my muscles to produce the necessary amount of force and the necessary amount of power with minimum activation of the muscles or minimum metabolic cost of the muscles, resulting ideally in like a lower whole body oxygen rate, lower whole body metabolic rate, and through that a more efficient, more economical pedaling technique. Okay? So that optimal path, that hypothetical like optimal set of joint angle trajectories during the pedaling cycle, is it necessarily one that's consistent with moving my foot through this circular path here, right? Not necessarily, right? Why would that path necessarily be circular? If we consider those highly nonlinear force length and force velocity relationships, even if we ignore like differences between muscles and between different individuals, why would that path necessarily be circular for a specific individual, let alone for every individual? It wouldn't necessarily. There's no reason ahead of time to assume that a circular path here, in terms of the path of where my foot here is going around the crank there, is necessarily the one that's consistent with the paths of the joint angles here that minimize metabolic cost or muscle activation or the necessary torques at the joints to move the crank at a certain velocity with a certain power or whatever your term of interest might be there. Okay? So what we might instead consider is, let me hop off here, a chainring here on the front that instead of being circular is some other shape. Okay, and why would that be beneficial? Remember the ratio of these gear sizes. The ratio of like the size of this gear in the front to the size of this gear in the back is what kind of influences your resistance to your pedaling and how much eventual kinetic energy you'll get out of the bike from the rotation of this wheel in the back. Okay? Remember, if the gear ratio here is like 3 to 1, like if this gear is 3 times bigger than this gear in the back, then you get 3 revolutions of the wheel for every revolution of the crank, and at a given pedaling rate, that's going to give you more horizontal speed. Of course, you'll have to pedal harder with more power, but it'll give you more horizontal speed for each rotation of the crank here. Okay. Now, when I have a circular chainring, when this gear up here is circular, and this gear up here is also circular, then that gear ratio is constant, right? The ratio of the size of this gear to the size of this gear is constant all the way around that pedaling cycle. It's never changing. So it's always the same ratio and always has that same relationship in terms of how many revolutions of the crank is resulting in revolutions of the wheel here. How many revolutions of the wheel I get for a revolution of the crank. Suppose this chainring was not circular. Suppose it was like elliptical in shape, like maybe it was squished in this dimension and like elongated in this dimension, or just kind of morphed in some way to have a different shape. Essentially, what that would be doing would be changing the radius of this circle here, like this distance there, so that it's not constant all the way around, but that it varies. Okay? Sometimes it might have a long radius at certain parts of the pedaling cycle, and at other parts it may have a relatively short radius. Okay? Essentially, what that would be doing is making the gear ratio not constant, but instead making the ratio of the sizes of these gears variable. The ratio will then depend essentially on where you are in the pedaling cycle. Okay? So sometimes at certain parts of the cycle you might want a big gear ratio, a lot of resistance to get a lot of revolutions here out of the tire. And at other parts, because maybe your muscles are operating at different places on their force length and force velocity curves, maybe you'd want a smaller gear ratio so that you have less resistance for turning the crank and don't get as many revolutions of the wheel for a revolution of the crank there. Okay, so hypothetically that could possibly make sense, that maybe the best shape of this gear up here for allowing the muscles to operate in kinematic situations that are most efficient or least effort or whatever term you want to use for some performance related index there that you want to make as best as possible. There's no necessary reason to assume that that's achieved with a circular chainring. Maybe it's an elliptical chainring that does that the best. Maybe it's a square chainring that does that the best. That's probably unlikely, but it's possible in reality. Or just some unusual shape that we may not even think of intuitively that would be best for that. Okay? So that's what these two studies were getting at and evaluating. Study number 1, again, used a computer model of pedaling. And what they did here was they defined a model here in figure 1 that is essentially the same type of model that we've talked about in the other computer simulation studies of cycling. They prescribed a pedaling motion, so the model had to pedal at a certain rate and produce a certain amount of power. That would be a reasonable amount of power for like a decently competitive road cyclist to hold for like an hour or so. And then they optimized the torques at the joints, at the hip and at the knee. The model they defined here had an ankle and a torque at that ankle, but the way that they defined it, the ankle torque actually ended up being a function of the hip and the knee torque, so it wasn't an independent free degree of freedom. So they were only optimizing here the hip and the knee torque. Optimizing the hip torque and the knee torque to get the model to pedal at the specified rate, which I think was 90 RPMs, and produce the specified power, which I think was 250 watts or so, while minimizing the squared, or the sum of the squared torques that it had to produce at its joints with its hypothetical muscles to perform that pedaling motion. So kind of a least effort cost function here, finding the torques at the joints that moved the joints in such a way that the crank rotated with the specified speed and specified power, with minimum torque at the joint, with minimum muscular effort at the joint. Okay. The interesting piece is they optimized not just the torque at the joints, so what the pedaler was doing, what the cyclist themselves was doing with their muscles to produce those motions and those moments at the joints. They also optimized the shape of the chain ring. Okay. It didn't necessarily, and this is a picture of the chain ring on their bicycle model here. The chain ring first was simulated as just being forced to be circular in shape, just like a standard chainring on a standard bike. Okay? Also then, they repeated a simulation where they were optimizing not only the torques at the joints to produce the pedaling motion, but also optimizing the shape of the chainring as a function of the pedaling cycle. Okay? And what was really being optimized there was the position of these little squares here, representing the shape of the chainring all the way around the pedaling cycle there, relative, or their location relative to the axis here, relative to the axis of the crank where you're spinning the ring around and producing the power that eventually gets transferred to the forward velocity of the bike. So they did the simulation once with a prescribed circular chainring, and then a second time where it could take these little points here, defining the shape of the chainring, and could move them around. Okay, each one of these points at each some incremental fraction of the pedaling cycle here, so some fraction of all the way around 360 degrees here for the pedaling cycle, could take those points and move them as to wherever it wanted, either further away from the center of the chainring or closer to the center of the chainring. So the option of having chainrings that were many different hypothetical shapes. And it didn't even necessarily have to pick a shape of a chainring that was physically plausible, right? Like you could envision if these little points here representing the shape of the chainring, if it was some very bizarre shape, then in reality, like maybe a chain couldn't even fit on that ring or stay on that ring and actually pull on it effectively. There were no constraints or restrictions on that in the optimization here. It could move these little points wherever it wanted in order to produce the lowest possible torques at the joints for completing the pedaling motion. Interestingly, even though it could hypothetically produce any shape of chainring it wanted, even one that would be physically impossible to make and use in reality, what it chose to, or what ended up being the optimal chainring shape for minimizing the torque at the joints needed to perform the pedaling, was this shape here, the kind of large white squares there, showing not a circular chainring, but what looks kind of like an oblong chainring, or like kind of almost an elliptical type chainring. Okay? What this did was it reduced the torques needed at the joints by, I think, around 1% or 2%, and that is what's being compared here in figures 4 and figures, all figure 4, sorry, three different panels of figure 4. Figure 4A here is the hip torque, and figure 4B here is the knee torque, and figure 4C here is the ankle torque. And let's just look, for example, here at figure 4B, which is the torque on the knee needed to complete the pedaling motion in the simulations with the circular chainring versus the non-circular kind of elliptical-ish chainring. Here on the x-axis is the crank angle, so where you are in the pedaling cycle. 0 is top dead center, and then you press forward down to the bottom dead center at 180, and then back up to the next top dead center at 360 here. So a full pedaling cycle, a full revolution of the crank. The black line is referenced joint torques measured on an actual human cyclist. The thin dashes, so this kind of smoother looking line here, is the torque produced when they tried to have the model pedal with the circular chainring with minimum joint torque. And you can see there, yeah, it's not exactly like the human torque was, but it's roughly similar in shape to the kind of the pattern of joint torque that the human produced. Then they repeated the simulation optimizing it to minimize not only the joint torque, which was what they also did with the circular chainring, but also optimizing the shape of the chainring. And there they got this line here for the knee torque with the non-circular chainring with the thicker, kind of wider dashes with the larger gaps here. Okay? So what is different here? When this torque is positive at the knee, when it's above 0, that means it's a knee extensor torque. That's your big, powerful quadriceps muscles producing that torque, which are arguably the most important muscle group in pedaling. Some people might say it's glutes. I would argue it's quadriceps. They're both important. But if you have to pick one or the other, I'd probably say quadriceps is the most important single muscle group for pedaling, at least for most cyclists. So what happened here? With the non-circular chainring, the peak torque at the knee was actually quite a bit higher. It was like maybe 20 Newton meters here for the circular chainring and up to about 30 Newton meters here with the non-circular chainring. But what it did do was notice here that for the rest of the downstroke, up here until the torque becomes negative, and now it's going to be more hamstrings than quadriceps, for the majority of the rest of the downstroke, the non-circular chainring, these wider dashes here, required considerably less torque than the circular chainring. So reduced the amount of torque needed by the big knee extensor muscles by quite a bit for a large fraction here of the main power producing part of the pedaling cycle. And you'll see similar trends there for the other big muscle groups here for the hip muscle, for the hip torque from the hip extensors, and the knee torque here from the plantar flexors. Similar trends there, where the peak torque is higher, but the overall torque that it needs for other parts of the pedaling stroke there is often a little bit lower. Okay, so it looks like here there might be a benefit in using a non-circular chainring, or maybe an elliptical kind of shaped chainring, rather than a circular chainring for reducing the muscular effort of pedaling and possibly improving through that the efficiency of pedaling. The second study here was an experimental examination of VO2, of the rate of oxygen consumption in trained cyclists, comparing a circular chainring to a non-circular chainring. Their non-circular chainring here was in figure 1, I believe. Yeah, here we go. And so here's the non-circular chainring. You can see it's not exactly an ellipse. It's kind of a skew morphed ellipse here, where it's kind of twisted around the center axis here a little bit, but definitely more elliptical in shape than it is circular in shape. Okay? So they had cyclists, trained cyclists, pedal on a bike, equipped with a standard circular chainring, and then with this more elliptical non-circular chainring. The motivation here is that if you do see a bike that has a non-circular chainring, it almost always looks something like this, kind of roughly elliptical in shape. You won't see a lot of bizarre other shapes. I think it's because this strikes a balance between possibly having at least theoretical benefits to performance in cycling, while also being something that's reasonably feasible to make without breaking the bank on manufacturing this really bizarre chainring that probably not that many people are going to buy. I don't know the sprint cycling community terribly well, but my impression is that there's these non-circular chainrings are more prevalent in terms of elite competitors using them in sprint cycling, in short sprint races, compared to using them in long distance cycling races like Tour de France and races like that. I still think you primarily see circular chainrings at that level of racing at the endurance end of the sport. So what did they see here with the circular chainring versus the non-circular chainring? Not much. It's highlighted here in some of the results in, I believe, a little further down, or perhaps further up in table 5 is the one. Yeah, table 2 through 4, 2 through 5 actually is the results of this one. Having a circular chainring versus a non-circular chainring. They've tried it at 3 different pedaling rates, at 50 RPMs, at 70 RPMs, at 90 RPMs. Tried it at several different gear settings, and no matter what they picked here, really didn't see any substantial or consistent differences in VO2 or in heart rate or in RPE or in the respiratory exchange ratio. So some of the classical indices here from exercise physiology of how effortful the exercise was, how much oxygen did it consume, how fast was the heart beating, how subjectively challenging did the athletes think the exercise was. Respiratory exchange ratio here, if you've ever done a VO2 max test, which some of you who've taken Kines 360 may have done one or at least seen one being done. This is one of the common indices that's used to evaluate if you're at like a maximum rate of oxygen consumption, like a really intense aerobic effort there. This is the ratio between your oxygen consumption and your carbon dioxide production. And if it gets above a certain value, it's usually an indication that you're near your maximum oxidation consumption. Anyway, regardless of which metric they looked at here, there were not any large significant differences between these physiological demand-related or performance-related variables and the chain ring used, whether it was the circular chain ring or the non-circular chain ring. No consistent improvements there in any of those variables. No consistent deprovements. It wasn't like they were worse off using the non-circular chain ring, but it definitely, on average, didn't seem to improve rate of oxygen consumption or heart rate or RPE or any of these things. So a little bit of a difference here. Seems like a hypothetical benefit from using non-circular chain rings in the first study, but then not actually realized in reality in the experiment when actual human cyclists pedaled on the chain rings. They used different outcomes here. The simulation study used a mechanical outcome, the torques at the joints, and the human experiment here used physiological measurements like VO2 and heart rate, which may not necessarily be reflected in the torques at the joints. Kind of like how we talked about a couple studies ago about how the demands on cycling and the reasons individuals pick like a certain pedaling rate may be possibly due to more mechanical reasons rather than due to physiological reasons necessarily. That's why we don't often see people pick the pedaling rate that necessarily rock bottom minimizes the oxygen consumption rate. They pick something that doesn't quite minimize it and is actually a cadence quite away from the cadence that minimizes the metabolic rate a lot of the time. Another factor that could be a big one here is that despite all that stuff I talked about early on in my video about the muscle properties, the force length and force velocity relationship, and how that has a big effect on how much force and power muscles can produce at certain places in the pedaling cycle, none of that was actually included in the optimization here. They had a very simple model of muscle here that didn't actually include force length and force velocity factors and things like that. Whereas in the human experiment here, when it has real humans with real muscles, those things are of course there. In real muscles, the length of the muscle and the velocity of the muscle matters in terms of how much force it can produce and how much activation and metabolic energy it needs to consume to produce certain power in certain situations and things like that. So it's possible they could have been missing something really important here in the design of the model and the simplicity of the model that makes a big difference in terms of why you might not see a benefit from a certain change in the chain ring shape here. But something that I think is worth considering and worth pursuing in reality, do the common designs of the equipment that we use in sports, is that necessarily best for performance, or might you benefit from deviating from those common designs a little bit? In theory, these things are relatively, I don't want to say easy, but relatively more common to observe in models like this. And in reality, sometimes we don't often see those benefits when we apply them to humans. Another thing that could factor in here is related to what we talked about earlier on in some of the running studies on the motor learning effect and the time course effect here. The model here has no motor learning in it. It's essentially already done all of its motor learning. The optimization process is kind of including that implicitly inside of it, where this is kind of the long-term effects of how this model would perform if it like trained for an indefinitely long time with this non-circular chain ring. Whereas here, these riders were presumably not super experienced with using non-circular chain rings. And so maybe if they practiced with them for a considerable amount of time, like some weeks or months or maybe even years, maybe the fact here that using the non-circular chain ring actually did not increase the VO2, maybe in the long term that would indicate that, well, maybe they would actually decrease the VO2. And if you look at most of these comparisons here, comparing here the circular chain ring on the top versus the non-circular chain ring, you can see that in a lot of the cases there was actually on average a small decrease in the VO2, right? It's not always the case. Like here's this one here where the VO2 actually went up by a tiny bit with the non-circular chainring. But for all these other ones here, it either went down by a little bit, or in some of these two ones in here in the middle, like especially at the 70 RPM cadence, it actually went down by quite a bit. A 0.1 liters per minute decrease in VO2 is maybe a pretty meaningful decrease in VO2 over a very long race. Okay, it just wasn't quite big enough here to reach statistical significance in this particular study. But maybe in the long term, as people practice with and use this non-circular chainring that they're less experienced with, they become more experienced, they kind of figure things out. Oh, okay, this is how I'm supposed to pedal on this thing that's most comfortable or most economical or whatever. And maybe we'd see some even larger reductions here in the VO2 that would reach significance and would result in an even more substantial and more meaningful influence on VO2 and possibly a more economical pedaling performance and technique. I'm totally speculating there. That wasn't included in this study, so we don't have any data confirming that. Just something to think about in reality when you see an immediate change in VO2 versus trying to forecast that out into a long-term training effect. Okay, that is it for today and it for pedaling. Next time we will move on to our final section of class on comparative sport biomechanics. Take a look at some impressive athletes in the animal kingdom. We will see you then.